For this lesson, we're going to be basically looking at the algebra that we use when we are evaluating limits and some of the different techniques that we can use to allow us to evaluate those limits. Before I get started on some examples, just some things for you to take a look at now, and I'll try to make these available to you in a note form or online so that these are some rules that you can use, and if you keep these in mind, most of them make sense to help you evaluate a limit. So let's just dive right in. The first of them is that if we take the limit as x approaches a of a constant, here k is some constant, any real constant, taking the limit doesn't change it. The whole idea of a constant is that it remains constant. So regardless of what x value I choose, so long as we're choosing an x value, so long as our value of a is somewhere on the domain, and again, for the case of a constant, the domain is everywhere, that's just going to stay constant. If we have something as simple as the limit as x approaches a of x, so if our function essentially is just f of x equals x, then as we get closer and closer to a, as x gets closer and closer to a, then the function gets closer and closer to a. So the limit itself is equal to a. Those two are fairly self-evident if you have any kind of understanding of what it is that we're doing with limits, and especially if you look at these things in terms of their graphs. Some of these later ones are a little bit less intuitive, and so these ones are worth taking a closer look at, but we're not going to go into a huge amount of detail over them. So the first one we have is if we have the sum or difference of functions. So if we're taking the limit of a sum of functions, so f of x plus g of x, or the difference minus g of x, it is often, not always, but it is often convenient to represent that as the sum of the limits. So rather than adding or subtracting the two functions and then taking the limit, what we can do is actually look at each of the functions individually and take the limits of those individual functions, and then we can add or subtract the result. So that's a valid way of doing this, and you can do this in either direction, whichever one of these actually works more conveniently for you. If I have a function and I'm multiplying it by some constant, in this case I've called the constant c instead of the constant k as I did above. If I'm multiplying by some constant, I can actually evaluate the limit separately of the function and then multiply that answer by c. Because you need to remember, something like this part, if we're doing our limit properly, in all likelihood that's just going to be a number or an answer. And so then it's going to be c multiplied by that number. Even if it turns out to just be an algebraic expression, it would be c multiplied by that new algebraic expression. If I have the product of two or more functions, and I'm taking the limit of that product, it might be more convenient to take the limit of the individual functions separately and then multiply those two results together. So the way you say this is, if I have the limit of a product, that is equal to the product of the two separate limits. Same thing works for a quotient. If I'm taking f of x divided by g of x, I have the limit of a quotient is the same thing as the quotient of the limits. And finally, we have the limit of a function raised to a power, and we can actually evaluate the limit of the function first and then take that whole answer and raise it to the power afterwards. And again, these work both directions, whichever is most convenient for you. Okay, so what we're going to do now is we are going to look at how we can evaluate these various limits, and we're going to use different techniques for each one of them. And that's not to say you could get examples that require actually multiple techniques to be used at different phases of the limit. But I've got these examples pretty much are going to focus on one technique each. So let's go ahead and start off with this first one. We've got the limit as x approaches 2 of x minus 2 over 4 minus x squared. Now you can see if you just try to mentally substitute the value of 2 in there, 2 minus 2 is 0. And 4 minus 2 squared is 4 minus 4 is 0. So we end up with this indeterminate form, 0 over 0. So we can't work with that. We have to do something else. Now, one thing you might see right away, especially with the way I've got this written here. I'm going to just rewrite out my limit, x approaches 2. And my numerator, there's nothing I can do with that. That's about as simple as I can make it. But this denominator is a difference of squares. So I can factor that as 2 minus x and 2 plus x. And by writing it that way, it might not be immediately obvious, but you should notice some similarity between x minus 2 and 2 minus x. Now there's a couple of ways on how you can deal with this. One of them is you've gotten to the point where you recognize how they interact with each other, and you can just go ahead and perform that division because they are the same factor, except for it's that question: how many times does 2 minus x go into 2 minus x, and how many times does it go into x minus 2? But if you're not quite comfortable with that yet, I'm just going to show you something just to convince you. I can take x minus 2 and I can write that as negative 2 plus x. I haven't changed anything there. And I can now factor out a negative 1 from that, and that becomes positive 2 minus x. And of course, I can convince myself that this is correct by reversing this. Multiplying negative 1 times positive 2 gives me negative 2. Negative 1 times negative x gives me positive x. And so this, and I wouldn't normally write this extra line, so I'll do it in red, but I'll show it to you. There's no harm in that. So you could also have written this as the limit as x approaches 2 of negative 1 times 2 minus x over 2 minus x times 2 plus x. And at this point, it's very clear that 2 minus x goes into each of those one time, and then I can proceed to my answer. But similarly, and I just want to show you, you could have expressed it this way as well. You could have recognized that 2 minus x goes into itself once, and it goes into x minus 2 negative 1 times. I'm still going to end up with the same answer, which is negative 1 in the numerator and 2 plus x in the denominator. So that's consistent across both of them. And so with that evaluation, I end up with the limit as x approaches 2 of, actually, yeah, I'm going to write it out one more time. And that becomes negative 1 over 2 plus x. You certainly didn't need to write this. You could have gone straight to our answer here. And now that when I approach x approaching 2 right here, I end up with negative 1 over positive 4. So the answer in this case to my limit is just negative 1/4. That was an example of using factoring in order to help us evaluate our limit. Okay, so in this case, we're going to take the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. Now this looks very similar to the one we just did. You might think, oh, it's factoring because I can now do something that involves this dividing out with this. But then when this divides out with that one, what do we actually get up there? So it's not quite so simple as that. So instead what I'm going to do is remind you about absolute value. So if I talk about the absolute value of x, what does absolute value of x mean? Well, the absolute value of x is actually most easily represented as a piecewise function. The absolute value of x is equal to just x, provided x is greater than or equal to 0. But if x is less than 0, if x is a negative number, then we actually replace it with negative x. And if we think about that, so what is the absolute value of negative 3? Well, in this case, it's a negative number. So that's the same as the negative of negative 3, because this is a negative number, which of course is positive 3. So that's why we write this as negative x. So that means that we have to consider this, or one way to do this is to look at it from two sides. And as it turns out, and I've selected this example for that reason, those two sides occur right here at x equals 3. So first of all, we don't want to deal with 0 over 0, so we can't go directly to substituting x equals 3. And we actually want to split this up for those two sides. So we could take this limit and we could write it as the limit as x approaches. Now, if we approach 3 from below, what is that going to mean to this? That means I have to take the negative of this thing over x minus 3. And the reason for that, let me just put the number line here, and I'm not going to do a lot with it, but if I put the value 3 here, if I approach from below, if I'm to the left of 3, what would be an example of a number that's to the left of 3? That would be, for example, 2. If I had x equal 2, which might be there, if I had x equal 2, 2 minus 3 is negative 1. So I have to take the negative of this whole thing. So imagine putting that in here. 2 minus 3 is negative 1, but the negative of negative 1 is positive 1. Absolute value makes this positive. So if I'm below 3, I have to use this definition. And if I'm above 3, let's take it over. The limit as x approaches 3 from above, well, then I don't have to change it, because if I'm above 3, for example, if I'm at 4, 4 minus 3 is equal to positive 1. That's like this case. I don't have to change it. It's already positive. So this just becomes x minus 3 over x minus 3. So I've got these two limits, but now, because I've had to talk about this from the left side and the right side, I can evaluate these limits separately. Now I've chosen this so that it now falls apart very readily at this point, because I've got the factor x minus 3 here, and I've got the factor x minus 3 here. They go into each other once, leaving me with an answer, the limit as x approaches 3 from below. My answer in this one is just negative 1. Negative 1 over 1, which is negative 1. On the other hand, when I approach 3 from above, I have the factor x minus 3, which divides out with the factor x minus 3. It goes into each of those one time. And so this one is equal to positive 1. But now I've got my two limits, which essentially is that the limit as x approaches 3 from below of f of x is not equal to the limit as x approaches 3 from above of f of x. So therefore, the limit does not exist. The overall limit does not exist. So that's this overall statement here does not exist. Because we've talked about this before, in order for a limit to exist, the two one-sided limits have to be equal to each other. So this is an example where we used one-sided limits in order to find out that in this case it actually does not exist. Okay, for part C, we have a kind of unusual looking numerator here. The denominator is quite plain, but the denominator is also a problem because we have the limit as x approaches 0, and we can't substitute 0 here. We end up with a division by 0. Actually, this one turns out to be an indeterminate form as well, because if we imagine substituting 0, we definitely get divided by 0. But we also, when we put 0 here, we end up with root 3 minus root 3 all over 0. And of course, root 3 minus root 3 is equal to 0 over 0. So that's not useful to us. We can't do that. But what we can do, and it's something I've referred to in a previous lesson, we're quite familiar with the idea of rationalizing denominators, but as I've mentioned before, sometimes rationalizing a numerator can be a necessary or a useful option. And so the way I'm going to do that is I'm going to take what's known as the conjugate of this numerator. I'm going to use the exact same terms, so root of x plus 3 and the root of 3 minus x. I don't change anything except for the sign between them, so that becomes plus. And I have to multiply both numerator and denominator by these terms. So 3 minus x. And now I'm going to go ahead and do the algebra, multiply this out. I get the limit as x approaches 0. And the way this works is, the reason why this works is where I'm rationalizing, I'm forming a difference of squares. I've got something minus something multiplied by something plus something. And so I end up with that first thing, which is x plus 3 square rooted, and that's going to be all squared, minus the next thing, which is 3 minus x square rooted, but that's also going to be all squared, divided by x times, well, that's just a multiplication. I'm going to leave that in the brackets. I'm not going to expand that out. So let's see what result we get from this. We get the limit as x approaches 0. The square root of x plus 3 all squared. We've got square root and squaring. Essentially, those two functions undo each other. Those operations undo each other. So in the numerator, we get x plus 3. And subtracting from that, we have a 3 minus x. All divided by, and again, this denominator is just going to stay the same. Not doing anything with it except for writing it out for now. And now we take a closer look at that numerator. We have the limit as x approaches 0. We have x plus 3, and of course there's a 1 in front of this bracket, so that doesn't change anything. So we have 1x, and I'm going to go over here, minus a negative x. So 1x minus negative x is 1x plus x, which is equal to 2x. And then we have 3 minus 3, which is 0. So the numerator turns into just 2x. The denominator, and you can probably see where this is going, the denominator remains unchanged, but now we have the benefit of the fact that x goes into x once and x goes into x once. So that gets rid of that problem we had, which was 0 over 0, in particular division by 0, but 0 over 0 in general. And so now we take our limit, and I'm going to write it out. You could probably go straight to your answer on this one. I'm just going to take one more line and write this out. So the numerator is not 2. The numerator is equal to, I wrote 1. The numerator is 2, and x plus 3 square rooted plus 3 minus x square rooted. And the limit as x approaches 0 of this whole thing becomes 2 over root 3 plus root 3, which is equal to 2 over 2 root 3. And we divide out those 2's. We end up with 1 over root 3, which we then rationalize, and that becomes root 3 over 3. And that's our final answer for this one. And so this one, we were actually able to solve, a little bit more algebra involved. We did this one by rationalizing the numerator. And our final example, and this one involves the technique that's going to be the most difficult for people to see immediately. We take a look at our situation. We've got the limit as x approaches 0. We've got division by 0, which is a problem. And when we let x approach 0, we get 0 plus 8. And then the cube root of 8 is 2. 2 minus 2 is 0. So we've got an indeterminate form, 0 over 0. And we've also got, this is very awkward, this is the cube root of x plus 8. So that's not something we would normally deal with. I've got something here that looks like it might, maybe I could do something with it, the minus 2, but I don't have any perfect squares, I don't have any perfect cubes, nothing like that. So what we're going to do is we're going to actually use a technique called substitution. Now, we've used this word substitution in many different forms throughout mathematics, even different years of mathematics. So in this case, my substitution is I'm going to take this term that's going to cause me some real trouble, and I'm going to substitute. So I'm going to say let u equal x plus 8 to the 1/3. I'm basically just going to say, okay, can I just get rid of this whole thing? It's problematic. Sometimes you get this right on your first try. Sometimes you have to fiddle around with it a little bit. So I'm going to get rid of this problematic term, but in getting rid of this, I'm getting rid of my x's. Now I have to take care of the x's everywhere else. Now this one's an easy enough replacement, but now I'm going to have to do some work in order to, for example, get rid of this x and to figure out this limit as x approaches 0. Well, that's got to change to be a u approaching something. So in order to do that, the first thing I should do is I'm going to take this substitution, which works for this first term. And now I have to rearrange it. So I'm going to cube both sides. So I end up with u cubed equals x plus 8. And then to isolate x, I end up with u cubed minus 8 equal x. So this first one allows me to substitute up here. This second one allows me to substitute here. And now the third thing I have to do is figure out that as x approaches 0, what does u approach? And as x approaches 0, u approaches 0 plus 8 to the 1/3, and 0 plus 8 to the 1/3 is 8 to the 1/3 is equal to 2. So that's like saying u approaches 2. And now that I've done that, now that I've asked myself that question, I've dealt with the limit part. So now let's go ahead and rewrite this as the limit as u approaches 2. And if you don't make all of these replacements, this doesn't work. You can't have any x's anywhere when you write this next expression. So we get a u minus 2 in the numerator, and we replace the denominator with u cubed minus 8, and we replace the limit value. Instead of x approaching 0, u is approaching 2. Now we still have the problem of 0 divided by 0, but now we have something we can actually work with, because in the denominator we have a difference of cubes, u cubed minus 8, and 8 is 2 cubed. So I can actually write this as, in a factored form, u minus 2, and actually let me just write to the side here just to remind you, a cubed minus b cubed can be written as a minus b times a squared plus ab plus b squared. So that's the factoring of a difference of cubes. So this is going to be u minus 2, and a squared is simply u squared. ab, it's plus ab, so that's plus 2u. And b squared, well, b was equal to 2, so that's going to be plus 4. And you can check this. You could expand this back out again to convince yourself that that's okay. Now, the reason why this is beneficial to us is because we've got the factor u minus 2, which goes into itself once, and it also goes into u minus 2 once. And so we end up with a final form, the limit as u approaches 2, of 1 over u squared plus 2u plus 4. And now we simply evaluate the limit, because we're not going to have any problems. You still have to be mindful of this, but it turns out when I go ahead and put u equal to 2 here, I don't run into any issues. I get 1 over 2 squared is equal to 4, plus 2 times 2 is equal to 4, plus the constant 4. And so that is equal to 1 over 12. And so now I've done what was a perhaps even impossible looking limit at first, because I'm really introducing this idea, this technique of substitution. But after doing that, we were able to resolve this one. So it did exist, and we found out what the value was. Okay, so we've done a couple of things. One of them is when you evaluate a limit, sometimes you can just go ahead and just evaluate the limit. I didn't bother showing that because really in terms of limits, that's a trivial case. If you can go ahead and substitute the value in immediately. Then we've got factoring, which I showed you in example A. We've got rationalizing, which was in example C. The idea of one-sided limits in example B. And I'm sorry, I said substitution. It was a substitution, but the proper name of what we did in part D there is known as a change of variable. So what we did is we actually changed the variable, and I really emphasized there how you had to change that variable in all locations. So this one is really, as far as this is really new, this is really important for you to give extra focus to when you practice on this, just to make sure you understand it really well. And as you can see, there is your assigned work related to this topic.